طيب بسم الله الرحمن الرحيم. So we talked about the ciphering mechanism. We said that in order for us to convert the plain text into ciphertext, we need to use two things. We need to use an algorithm and a key. Okay, so we apply the algorithm. Using the key, we convert the ciphertext into the plain text into ciphertext, and then for decryption we do the other way around. So largely we can divide the ciphers or the ciphering algorithms into two major categories. One is what we call substitution ciphers. Substitution ciphers, they take one or more letters from the plain text, and they transform it into another letter. So you take one letter or two letters from the plain text, and then using the key will give you the information how to transform that into another corresponding letter in the ciphertext. So this can be good.
So the algorithm, according to what you just said, the algorithm for encryption and decryption doesn't have the code on how to transfer the actual text.
It does. Well, the algorithm has the code. The algorithm is constant. It's fixed.
But the key,
okay, and then it uses a different key by plugging in the key into the algorithm will be able to convert to the ciphertext. So the substitution cipher can be divided further into two types. One is the monoalphabetic, and mono refers to one. So it's a one-to-one relationship. So I take one letter, convert it to one letter. As simple as that. The other one is what we call polyalphabetic. So we take two letters or three letters, and then we convert it into using the key into another. So it's we can consider it one-to-many or many-to-many relationship. The other category is the transposition ciphers, and transposition ciphers will be efficient for large text, and the transposition meaning that you change the location of the text, but you don't have to transform it into something. Okay, so this one we will not go through. We'll go through the first two types quickly. So basically, so the plain text is in that case is hello. Okay, and this is the ciphertext. So we can see, we can guess that from the plain text and the ciphertext, we can see that L and L is converted to O and O. E is converted to H, H is converted to K, O is converted to R. So it looks like it's a monoalphabetic algorithm, as simple as that. And of course, this transformation can be given in the key. So basically, the key could be as simple as you assume that the letters are sorted alphabetically, and then the key will be something like this. Will be like K, O, Z, R, and so on. 26 letters. This means that A will be converted to K, B will be converted to O, and so on. So this is an example of a key. A key is 26 letters, and as simple as it tells you what corresponds to this. The problem with this one is that the key is pretty long. The key is 26 letters, and if you have more letters than the A to Z kind of alphabets, then the key has to be even larger. Okay, so in that case, we need another algorithm that potentially can use a shorter length of keys, which is the one that we will talk about in the next slide. So before that, this The one problem here is that if you have O and you know that this is a monoalphabetic algorithm, chances are you can try to, through the traffic analysis, you can try to do the guessing, faster, and you can probably reach to breaking the key and knowing the key faster. If you have many-to-many relationship or one-to-many relationship using the polyalphabetic algorithm, then the different combinations of the key, you can use 2 letters or 3 letters or 4 letters, so the traffic analysis will be much harder in that case, because you don't know how the letters are broken, okay, and you don't know that, so you don't know how what is the size of each group. Okay, so it could be 2, it could be 3, it could be 4, you don't know. Okay, and you also don't know the key. So that makes it harder and harder. So here, as we can see, the hello is converted into this text where LL is converted into NZ. So we take each 2 letters and we convert it into other set of letters. Okay, so in that case, you may not have any repetition in the ciphertext, and you can break the text into subgroups with some grouping, with some specific grouping that you are the only one who knows about that. So to make the breaking of that key much harder. As we said before, we work based on the fact that the algorithm itself is known. The algorithm may be public and it's maybe known, but the key and the way that you do the ciphertext makes it harder and harder for Eve to break and get the key. So one example that tries to fix the problem related to the size of the key, instead of just having a key of 26 or more letters, there is a cipher called Additive Cipher, or sometimes they call it Shift Cipher. Okay, or sometimes they call it a Caesar cipher. Caesar because Julius Caesar used to use this simple algorithm to communicate with his officers and stuff in the past. So it's named after him. The idea here is that the key is very short. It's actually it could be like one number. The key is as short as one number, and it gives you the shift in the alphabets. Okay, that this letter corresponds to. So how is that? So first you select a key, anything anywhere between 1 and 26, and usually they select the odd numbers, and we'll talk about why. So the key could be like 1 or 3 or 5 or 7 or 9 or something like that. Okay. And then all you need to do is just to take one letter from the plain text. And each letter here corresponds to a number. So as we can see, A corresponds to number 0, B corresponds to 1, and so on. So we have from 0 to 25. Okay, so it's a modulus 26 number. Okay, and then all we need to do is just to take from the plain text, we take one letter, we get its number. So assuming that it's I, for example, we get the I. We add to it the key. Okay? So we add the key to it. Let's say the key is 3. Okay? So we add 8 plus 3 is 11. And then we take the modulus with respect to 26. Because we need, at the end, we need 26 letters. So if for example, you select 24, 24 plus 3 is 27. Okay? So you have to convert it to a number from 0 to 25. So in order to do that, you take the modulus with respect to 26, which means that you for 24 you take 3 You shift it by 3. 1, 2, 3. So it's like you are circulating. Okay? So it's very simple. Whenever you have any letter, you just shift by 3. When you come here, you shift by 3 by a circulating. And that's done through the modulus operation, as we will see. So in that case, the encryption is very easy. You take the plain text, one letter, because this is monoalphabetic. So you take one letter, you add to it the key, and then you take modulus 26, assuming that we're dealing only with the A to Z letters. Okay. For the decryptor, it's the other way around. So you take the number, you subtract it from you subtract the key from it, and then you take modulus 26. I should also yeah.
Isn't this easier to attack?
Yes, it's easier. You're right. You're perfectly right. You're perfectly right. If I know that this is monoalphabetic, and I know that this is an additive or shift cipher, then it's easy to break, because if the key is short, then instead of trying to guess what each letter corresponds to, I will use another way. I will assume that the key is 1 and see if that leads to a logical text. I will assume that the key is 2, so it's much faster in that case. Whereas for the first case, if the key is larger, then I have to do lots of combinations in order to break and know the exact key. So in that case, it's much harder. So okay, so the decryptor is the reverse operation, and I have to point here that if this result is negative, then you have to add to it 26. So it doesn't work that C, for example, is 3 and the key is 7. So you say it's minus 3 modulus 26. In that case, you have to add 26 to the minus 3. Okay, which makes it 23, and then you do the modulus 26. Okay. So some example. So the additive cipher it's very straightforward. So assume that we want to convert again the text hello using key 15. Okay. So in that case, we apply the shift cipher on the encoder side, or on the encryption side. The H corresponds to 7, E corresponds to 4, L corresponds to 11, and O corresponds to 14. So all we need to do is just to say 7 plus 15 modulus 26. And we do this for all these letters. The corresponding so the I don't know why it's doing this. So the corresponding thing now is WTAAD. Okay. So using only short length key, we can convert, and we can do the monoalphabetic cipher. And as we said, this is breakable, and it's easily breakable by just guessing the key. If we know that the key is from 1 to 26, it doesn't take us a very long time to break it. Okay. So the decryptor what it will do is that it will do the reverse operation. So we'll take W. W is 22. So we subtract 15. So in the decryptor we subtract 15, and then we do the modulus 26. If the process here is negative, like 0 minus 15, then we have to add 26 and then modulus 26. We convert this into the original number again. Any confusion here? It's very, very straightforward. Yeah. Very straightforward operation. Okay. So in order for the traffic analysis, if we put ourselves into the situation or the role of Eve, so now we are bad guys and we want to attack and guess what the key is, then all we need to do is just to listen and get any ciphertext. When we get any ciphertext, then our criteria in that case will be, when we convert it to the plain text, we get something that looks reasonable. Okay, this is the only way for you to know whether you have guessed the right key or not. Okay, so if you get the ciphertext, then you try with key 1, and then you see what text you get. Okay, so you know the algorithm. You know that the algorithm that was used here is monoalphabetic. So you know that, right? So you apply this algorithm on the ciphertext, and you keep getting text like this until you see that the text that you get is something like this. Not very secure. So this looks like a right sentence. So then you take this key, which is 7, and then you listen to more ciphertext and you apply the same key. Do you get some logical text? So that confirms. Sometimes they use some probabilistic techniques. So if you get more logical text, this means that there is a high probability that this is the right key. If you use this key on a different text, because sometimes it happens by coincidence that you get a sentence that looks logical, even though it's not the right key, right? So if you get a logical sentence, this means that this is the key with higher probability. You try this key to other ciphertext, and if you get logical, then the probability will be higher and higher, and so on. Okay.
For example, if we apply this twice on the same text, will it be more?
That's a different algorithm. This will be a different algorithm. So you can apply the additive multiple times. That's your question, right?
Yeah.
So this will be a different algorithm. Could be, yeah, sure. You can do that. But it's for this particular case, it's as if you have used a key which is equal to k. Right?
So it's still mono.
Yeah, it's still mono, yeah. For this case, for the case of additive, because if you shift 3 and then you shift 3, this means you shifted 6, which means that you have used a key which is 2k. Okay. So another type in the same category, which is what we call the multiplicative cipher. So I mean, if we can use the summation, I mean, why not use the multiplication? So it's easy. And the idea here is, again, when we multiply, we have to do the modulus 26. This means that whatever number we get after the multiplication, we have to get a number between 0 and 25. Okay. So in that case, the key needs to be, and this is very important. The key needs to be an odd number. Why is this? Well, we know that the numbers from 0 to 25, or the characters or the alphabets, they take numbers which are from 0 to 25. So some numbers are even and some numbers are odd, right? So what is the result of what we know from normal math?
It will be 0 always for the even numbers.
Hmm?
It will be 0 for the even numbers.
Yes.
Not 0. I mean, why?
Will be 0. Because 2, 4, 6, 8. But for some.
So the idea here is that why the key has to be odd? Because if we take even, times even, that's even, right? If we take even times odd, even times, okay, even. Okay, if you and then if you take odd times odd, that's odd. Okay, right? So if we assume that the key is even, this means that we're talking about these two cases, right? So the result will be the result will be even regardless. So this means that whatever the plain text is, we will have to convert this text into letters that have even number, which means that we will not have all the text in the ciphered side, on the ciphered side. يعني بمعنى صح يعني two letters, one is odd and one is even, and then you may correspond to the same letter in the cipher text. Because even times even is even, and odd times even is even, right? So two different characters on the plain text side may be transformed into one letter in the cipher text, and that's not good, because this way it's not reversible. You cannot reverse it back, right? So that's why we need to have, if you try it with odd numbers, if you try it with odd key, so odd times even is even. Odd times odd is odd. So you end up with the same type like the plain text. If the plain text is even, the cipher text will be even. If the plain text is odd, the cipher text will be odd. So in that case, you can have all the combinations in the cipher text. So that you will not have two letters that get transformed into one letter in the cipher text. And that's a very important characteristic, because otherwise it's not reversible. We cannot decode it. If we have A and H corresponds to K, for example, we don't know what K corresponds back to. We have no idea of knowing that. Okay, so that's a simple thing that we have to make sure of before we run this simple operation. Okay.
So that's why you take prime numbers, because prime numbers.
لا, prime numbers is something else. Prime numbers, يعني this is much more complicated than this. Okay. Here they are just odd numbers, and then the process will be similar, exactly similar to the one before. We take this number, we multiply it by the key. The key here is 7. Okay. In that case, the key is 7. So 7 times 7 is 49. 49 modulus 26. Does anyone not know how to do the modulus?
No.
Okay, it's easy, huh? Okay, so it's the remainder of the division operation. Okay, so 49 modulus 26 is 23, and because the division result is 1 and the remainder is 23, so the remainder is 23. 23 corresponds to letter X. Okay, and so on. 4 times 7 is 28 modulus 26. That's 2. And 2 corresponds to C, and so on. Okay, C because we start from 0. Okay. So this, so if we take the same key and we try the additive or the multiplicative, the cipher text will be different. Okay. So you have to know both. You have to know the algorithm and you have to know the key. Unfortunately, the algorithm can easily be known. It's sometimes announced, it's published, everyone knows about it. So the only challenge is to know or to guess how the key looks like. Another thing to pay attention to is again, I mean, when we on the decryption side, when we divide, you cannot have something like this. So let's say like we have D, or the P here is 4, and we divide by 7. So modulus 26. Okay, so what is we want to know what is this letter. Okay, let's take let's say 2 here. Okay, 2 divided by 7. How do you do that? So this number has to be integer number. Okay, this number has to be integer number because this is the result of the division on the encryption side. So here this number has to be integer, which means that this is a fraction. We cannot leave it like this. So the only way we can get around this is that you have to add to it 26. Okay, you have to add to it 26. So 26 plus 2 is 28. Divided by 7, that's 4. So 4 will give you the E. Okay? So similarly, let's see. Yeah, so even to 20, let's say 20. 20 divided by 7. It's not an integer number, so you have to add 26. Right? So it's 46. 40?
Yes. No, to add 26, yes. So 46.
So 20 ولا
46.
So it's still not integer. So you have to keep adding. Yeah, you have to keep adding 26 to it.
We can add only 8, right? Can't we just add 8?
La. You have to add 26. You have to keep adding 26 until you get an integer number. So 26 plus 26 plus 20. If the result is not integer, you keep adding 26 and so on. Until you reach to, because this is 14, so you will have to keep adding 26 multiple times. Okay, so that's the way you do the decryption side. So the key is that the result of this part has to be integer. Okay? Any questions?
There's no slide about decryption of this algorithm? Like,
Sorry?
Mafi slide.
No, there's no separate slide. That's why I'm explaining that. So any questions?
So it's not in the ground up there? It's not...
It is.
Yeah.
Right, so this is how you do it. So P times K to the power minus 1, which means P over K.
Yes.
Right? So you have to divide. Okay?